This is the Golden Eye of James Webb Telescope, an eye which NASA has bet over $10 billion and 20 years for you to see the birth of the first galaxy, 13.5 billion years ago. This is a huge international collaboration between NASA, European Space Agency, and the Canadian Space Agency. James Webb Telescope is going to be the world's most powerful telescope. In fact, it will be 100 times powerful than the Hubble telescope. And fun fact, here on Earth, it could detect the heat signature of a bumblebee on the moon. Now put that telescope in space and set it on a mission to find stars 10 billion times more faint than stars we can see with our naked eyes. Stars that were formed in the early days of the universe. The Big Bang. The James Webb Telescope is going to be the successor of the Great Hubble Telescope, but James Webb Telescope will be mostly capturing infrared light, while Hubble captures optical and ultraviolet light. So what is infrared light, one might ask? Well, we can't see it, but we can feel it as heat. On the electromagnetic spectrum, infrared light lies right outside the visible light section as longer and linear wavelengths. You have probably seen infrared light in remote controls and even temperature guns commonly found during the COVID-19 pandemic. So, why does JWST use this infrared? Dust. Yes, you heard me, dust. You see, space is full of dust. Astronomers don't really know exactly where the dust comes from. But what they do know is that around 47 metric tons of dust fall onto Earth every year. And they also know that supernova play a huge part in its production and distribution. So when stars and planets are forming, they're hidden by clouds of dust that block visible light, but it doesn't block infrared light. This side by side from NASA shows just how much more you can see when you are measuring infrared. There are whole new galaxies that come into view, and because the universe is expanding, the visible light from the early universe gets stretched into infrared, and that's called cosmological redshift. It's this cosmological redshift that Webb's opticals will be hunting for to uncover the story of the early universe. The telescope core superpower comes from its advanced optical system. James Webb's eye, otherwise known as the optical telescope element, consists of 4 ultra-reflective golden mirrors and dozens of subsystems to support the massive optics. The mirrors are gold because it has a very high reflectivity in infrared. Out of the 4 mirrors, it's the primary one that really stands out. That's the first mirror that light hits. And in this case, there are 18 segments that are hexagonal shaped, which means each mirror actually acts as a separate telescope until they are aligned in space to work as one. All 18 hexagonal segments and additional mirrors are made of beryllium, a strong and lightweight metal that holds its shape at cryogenic temperature. Remember, space is warming -207 degrees Celsius. Webb's primary mirror is 6.5 meters in diameter, which gives the telescope more than 6 times the correcting area of the Hubble's telescope. It's like correcting raindrop. The bigger the bucket, the more water you're gonna correct. The first mirror, the primary mirror, will be the first to correct light from distant universe. The light then converges down to the secondary mirror. The secondary mirror continues to focus the light, and then the light reflects to the tertiary mirror. And then finally the light sent to the fourth mirror, which is the fine steering mirror. And the purpose of that mirror really is to collect slow drift between the telescope and the spacecraft. After all that, an image is created as light enters the 4 scientific instruments. These scientific instruments and the 2 detectors on the Webb will allow you to study near-infrared and mid-infrared wavelengths. The near-infrared cameras host on-board coronagraph that can hone very faint objects even if they are nearly extremely bright lights, similar to how you would hold your hands up from the sun to see another object. Then there's near-infrared spectrograph, which has a unique technology to analyze the spectrum of an object using microshutter array. This contains 100 microshutter cells, measuring as wide as a human hair. This technology reveals the physical property of the target, including the chemical composition, mass, and temperature. Next up is the mid-infrared instrument, which uses onboard cameras and, you guessed it, mid-infrared light to provide amazing images, even more impressive than that of the Hubble telescope. And finally, the fine guidance sensor, near-infrared imager, and the filtrate spectrograph will actually find targets, investigate exoplanets, and detect fast light within star system. Because the telescope is capturing infrared light, it's super sensitive to heat. In fact, it's designed to operate about 40 degrees above absolute zero, and that's where the tennis court size sunshield comes in. It has 5 layers separated by vacuum to protect the telescope instruments from the sun's heat. Right now, there is no any rocket in the US that can carry this telescope because of the failing size, so this telescope has to be folded up origami style and stuck on top of the Ariane 5 rocket, and it will launch in European Space Agency spaceport French Guiana. The telescope will be heading to the second Lagrange point, 1 million miles away from Earth, or 1.5 million kilometers. Putting this telescope at the second Lagrange point is important because this orbit is stable and it's able to observe the universe without having Earth and the Sun being your field of view. Despite its launch being delayed for more than 7 years, but on 24th December 2021, is going to happen. And this is one of the most complex projects that NASA has ever built. So why did I call this a bet in the beginning of the video? Yeah, for example, the middle of JWST, NASA says that any variation in their shape has to be smaller than the wavelength of the light they are observing. So less than a fraction of the human hair. Problems with the Hubble mirrors meant that it had to be repaired in space. But you can't do that when you are a million miles away from Earth with James Webb Telescope. After launching, the Webb will take 30 days to reach its destination. After its arrival, it has to unfold perfectly. A telescope-sized sunshield with 5 layers had to deploy to keep the telescope cold, and this process will take This whole process will take 6 months. Everything has to go accordingly for the telescope to work. My favorite observation of the James Webb Telescope is going to be the exoplanet, in order to understand the composition of their atmospheres. So if we want to see another pale blue dot elsewhere, then James Webb Telescope is our best hope. Thanks for watching Point Nemo Team Minus James Webb Telescope episode. Be sure to subscribe to our channel for more videos like this. My name is J Max.